Video, we're going to have a look at as an introduction to computational thinking. First of all, what is it? Well, let's start by saying what it's not, in fact. So computational thinking would suggest that it's how computers think, whereas in fact, computational thinking is about how we solve problems that can be used and solved on a computer, and some different skills that we can use to do that. We're going to look at something called abstraction, which is when you look at problems from different sort of views and you perhaps remove information from the description of the problem. We're going to look at decomposition. This is when you break a problem down into smaller parts that are more manageable. So if you imagine a very large problem, it can easily be broken down into parts that either different people could do or could be solved by a single person. Often when we're solving problems, we have patterns within them that we can use to help us solve them, or we can use other techniques that have been found that follow the same pattern that is in our problem. Finally, we can think about algorithm designs and sort of putting our problems into words and flowcharts, etc., to help us solve these problems. Okay, before you get started though, I think we'd like to have a little look at just solving some problems before we even talk about these. So I'm just going to have a little introduction here to something called the Ocado Rapid Router website. You probably know Ocado as the company that delivers your groceries to your house. But have you ever thought of the technology that goes behind picking all of the different items? You can see here cameras and robotic arms to be able to pick up fruit without squeezing them and things. Lots and lots of different problems that need solving using computers. So Ocado has developed a website called Rapid Routers that we can use to try and develop our problem solving skills. Let's have a quick look at seeing how we can solve one or two of these problems to get you started. We'll just pick one here and see what they look like. Okay, in this case, the task is you've got to get the delivery vehicle from the warehouse to the customer's house, and you've got 3 different types of blocks you can do this with. Let's just randomly see what happens if we pick some blocks. Disaster. Okay, so what we've got to do is we've got to think about the problem and determine what we need to do. Fairly straightforward for this one. We can see by looking at it, we have to move forward a few times, then we'd do a turn to the left, a turn to the right, then forward again, and then another turn to the right, and then move forward a few more times before eventually we need to do a turn to the left. Okay, and then we can see what that would look like, or we can put it on faster, one more way to the end. There you go. That's how we can solve a problem using Rapid Router. We're going to let you have a go at solving different problems, and you will need it for some problems to use if statements to make different choices as you're solving the problems. So I just want to quickly show you how you can customize the if statements. So instead of just having one if condition and doing something, you can perhaps say if the condition is true, do one thing, else do something else. Or we could have an if with one condition and an else if for another condition, and then with a final else clause at the end. So you might just need to do that. Okay, off you go, solve some problems. Okay, so what I'd like you to do now is, if you're using a workbook, you can go and follow the links to these starters. And if you're not, if you go to the Rapid Router site, you can have a look and see problems 13, 20, and 34 all require you to have some different use some different skills to solve these. Okay, for now, I suggest if you're going off to do these, you pause the video, and I'm going to show you the solutions when you come back and replay the video. Okay, here were the 3 different solutions. The first one just required you to perform a sequence, pretty much like the demonstration we had earlier, and we just kind of went through in a sequence of lefts and rights and forwards, etc., to solve the problem. The second one, we saw that there was a kind of a pattern in there that we could use, and we were able to sort of use a loop this time to solve this problem. And finally, the third one, you need you to think a little bit about the algorithm that required to solve this with the blocks that you had, and required you to use several if statements and checks to see if you're at the destination with some loops in order to do that. So whether you deliberately applied any computational thinking skills or not, you were using those to solve these problems if you did solve them. If you didn't solve them, don't worry about it. Hopefully by the end of this video, it might give you some ideas of how some different ways that you could approach these problems in order to help you to try and solve them. Okay, talk about abstraction now. And this is this idea of looking at problems in a different kind of way, often removing unnecessary kind of information from the problem. So a good example of this is when we use maps, such as a tube map here. Obviously, the lines in the underground station are not straight lines, and they're not all equally spaced out, etc., as they're shown in this map here. So it's kind of a different view of the real world, but that helps us solve the problem. How do we get from one station to the next? You did this a little bit when you were doing the rapid router tests tasks. You probably weren't thinking about the fact of vans going from a warehouse to a customer premises. You were just looking at the patterns on the road and the blocks that you had available to you. So this is something that we'll often do without even really thinking about it. But sometimes if a problem gets quite difficult, it's important to sort of stand back and look at it in a different way, and see if we can kind of solve it using a different sort of technique to how we first looked at the problem. And this will often require us to remove information from the problem. Okay, so we're going to get you to try a task now. Again, if you're using workbook that goes with this video, I'd like you to have a go at doing this task. Before you actually just solve the problem and work out what the answer is, I'd like you to see if you can cross out all of the information in this description in the box here that is unnecessary in solving the problem. So once again, I'll pause the video and give you a time to go away and solve the problem before showing you the solution. So here we go. A lot of the information there was just not necessary. The fact that it was Joe and Anne driving a car from London to Oxford made no actual difference to the problem that we were solving, or which roads they were using, etc. What really was important was that we needed to know the distance that was travelled. We needed to know how long the journey took. And from that, we can work out what the average speed was by getting the miles and dividing them by the hours. Okay. So next, a different kind of skill that we can use to solve problems is decomposition. This is when we take a large problem, we break it down into smaller parts. And there's an example that I've used here from the BBC Bite-Size website that says when a policeman is trying to solve a crime, and they don't do it all in one go, they will kind of do it in small parts. And have a little look to see what the crime was that was committed, when, where, is there any evidence, are there any witnesses, have there been any other similar crimes kind of recently, and use a combination of all of those different parts that they solved individually in order to try and hopefully solve the crime. This is a common way of just taking complex things, breaking them down into manageable kind of chunks, and then solving those chunks individually, and then perhaps integrating and joining all of the sort of the answers together to get a final solution to the problem. Okay, so once again, I'd like you to have a go at trying to use this skill. So the task says, imagine you've been given the task of developing an online language learning quiz site for multiple users. So you can imagine this is something like Duolingo or some other sort of app that you can load onto your phone to try and help you learn a new language. And obviously this is a big problem. There's a lot of different parts to this. So could you see if you can list at least 4 different parts of the system? You might find you have quite a few more than that, but at least break it down into 4 parts. Okay, once again, if you're solving this using a workbook, you should pause the video now, and I'll give you a chance to go away and come up with your answers before showing you some suggested answers from me. Okay, these were my four main parts. As I say, it's a big system. There's probably a lot more parts to it. But if we think about it, the key parts are getting the questions, looking to see if answers are correct. If it's a multi-user system, we're going to need a login system. And then we're going to need a database and some way of storing all of the data for the questions, the answers, and the scores themselves and the information about the users. So they're four of the key parts to this system. You might have come up with other ideas about the user interface um, and sort of how you present the information, etc. But again, it's important that what you do is you break the problem down into manageable pieces that you can solve kind of individually. The next skill we can use is by looking at patterns to see if we have patterns in problems. Patterns that they're all around us. Again, if we're able to spot these patterns, it's a good skill to help us solving our problems. So when you did the rapid router practice tasks earlier on, hopefully you spotted that there was a pattern in solving that one, and you had to just do turn left and turn right multiple times to get from one place to the other. We often find that these sort of patterns appear in other problems, but we can then sort of reuse some of the solutions to those other problems and apply them to the problem that we're working on. A good example of this is, although they look something completely different, the pictures here show us a social media graph of how people know each other, or sort of friendships exist between all of our friends on something like Facebook. And then if you look at the structure of the information that's used when you are perhaps doing a routing sort of problem like navigation, these could be flight paths or something with times between different airports. But actually, if you look at them, they're quite similar. We have this same idea of what's known as a graph structure. And the way that you would sort of move around from one airport to the other is pretty much the same idea as how you would kind of navigate to find out who your friends of friends. So a lot of the skills from one of these problems can be applied on the other problem as well. Okay, the last bit that we're going to look at is something called algorithmic solutions. This is when we have probably done the other stages first. What we're going to try and do is describe a set of rules. That's all an algorithm is. It's a set of rules that can be used to solve a problem. We're certainly used to this idea of cooking with recipes or following instructions to build furniture and things. We think about what they are. They're just a list of instructions of what we need to do in order to solve that task. Essentially, what an algorithm is. However, when we use computers to do them, we need to often be a little bit more precise, and computers need really clear instructions. And two ways that we can do this is using something called a flowchart, or write something called pseudocode. So before we actually begin real coding, we just kind of get a rough idea of the structure of what our programming languages are going to use. Most programming languages follow a similar kind of construct to them. And whatever we kind of do at the flowchart and pseudocode will work for most programming languages. Okay, what we've got here is we've got another task for you to do. There's a flowchart on the right there. I'd like you to have a little look at that. So even if you've never really studied flowcharts, I'm hoping you could follow the flowchart and the flow. Obviously, you start at the start and kind of go through the blocks in different directions. And that is a flowchart to solve a particular problem. So there's two things I'd like you to try and do this time. Is one of them is to determine what the purpose of this flowchart is, what the algorithm is trying to achieve. And then second thing is to see if you can work out what the different style of the blocks are that have been used in the flowchart and match them up to the words on the slide in front of you. Okay, once again, I'll pause the video, or I suggest you pause the video whilst you go away and solve this before I pop the answers up. Okay, the purpose of the algorithm was simply to determine if you've made a profit or a loss. And here are the symbols. We've got input and output. So this is where we're perhaps getting information from a user or we're printing something out. We have a decision within our program where we're going to make a different choice. And depending on a decision, we will carry out different instructions. As our programs are running, they're processing data, and this might be calculations or storing information away. And these are known as processes. And then finally, we had some start and end kind of blocks to show us when our program begins and where it kind of ends. That's the common symbols that are used in a flowchart. Okay, going to show you a short video here, which is an example of trying to use all of these different skills to solve a problem, to find the sum of a series of integers. Okay, got a problem to solve. What are the sum of the values 1 to 200? So 1 plus 2 plus 3 plus 4, etc. Well, the actual answer to this one is 20,100. Okay, but obviously as a human, to try and add those all up would be kind of impossible to do in your head. If we've got a computer to do it, how would it perhaps do this? Well, you could start by breaking the problem down into smaller parts, decomposing it. We could do 1 plus 2 equals 3. We can add the 3 into the 3. You add the 4 onto that, etc. And if we repeated that 200 times, all of the numbers all the way from 1 up to 200, we would get the same answer. And that would work, but a computer for really large values instead of 200, like 2000 or something, starts to take quite a lot of time to solve that problem. So if we try and think of the problem in a different way, we can use some abstraction to think, well, could we halve the number of times? What if we did 1 plus our 200 gives us 201, 1 plus 2 plus 199 gives us 201, and 3 plus 98 also gives us 201, and then we'd only have to do this 100 times because we're adding two numbers together there. Obviously, we'd then need to multiply the 201 by the 100 to add them all up. But if we think about what's happened here and we have a little look at it, we've actually got some patterns appearing here. We've got some values which are constantly changing there. Okay, but what we can see is that this part here, it always equals 201. And obviously we were going to say we would multiply the 201 by 100 to get the final answer. So if we think of this in a slightly more algorithmic way now, and looking at these patterns, what we're actually saying is that if we change the 200 to just be n, to see if this would work for other values, we're saying we've got here, we've got 201, which was n plus 1, okay, and then we're timesing it by 100. Well, where does the 100 come from? Well, it was half of whatever we had, so it's times n over 2. And does that work then just by performing this sum once here? Well, so we've got 201 over 200 by 2, so that's 201 times 100 gives us our 20,100. So what we've managed to do here is by applying some decomposition, breaking the problem down into parts here, and then looking for patterns over there, and a little bit of algorithmic thinking, we've now just come up with a much better solution than what we started with at the beginning. Okay, what I'd like you to do is have a little look now at an implementation of the algorithm that was used to solve the problem. There's two versions of it in the Scratch program. The first part of the program here is doing it in an iterative kind of way, the way we started at the beginning of saying we would go round a loop, say 200 times, and add on the value each time we go around. So we're just counting up to add our 1 plus 2 plus 3, etc. And that's the main loop kind of there to solve it. And then it would tell us how long it took to solve that problem. And then the second sort of solution here is the final one we ended up with. And what I'd like you to do is just try and run this program. Um, Give it different values, perhaps of 100,000 or something, and you can see that it makes a huge difference to how quickly the computer was able to solve the same problem, but doing it in different kind of ways. Okay, I'll pause the video there, and again, if you're using a workbook, you can follow the link to that Scratch application and run it and see what happens. Okay, that's sort of finishing off our introduction to algorithmic thinking. We've looked at the four main kind of steps of computational thinking of our abstraction, decomposition, patterns, and algorithmic sort of thinking and design. Why don't you go away and have a try now and solve some problems that will require you to apply this computational thinking skills. So I said at the start, it may be that you just use these naturally without kind of needing to sort of think about what they are. But there may be other times when the problems get a bit tougher that you have to start stepping back from it and applying one or more of these different skills in order to help solve the problem. Thanks for watching. I hope you enjoyed the video. Thank you.